Hello, I'm Dong Choi from Sungkyunkwan University of Software Engineering. I'm going to present this paper, Automated Feedback Generation for Multiple Function Programs. This is the outline. Recently, the demand for online lectures such as massive open online course has increased due to the coronavirus. Among them, the most popular programming course provides students with coding assignments. However, personalized feedback cannot be generated because there are too many students compared to the instructors. Therefore, automated feedback generation was proposed. The feedback generation process of AFG is generally divided into 4 steps. The first step is dividing student submission into correct and incorrect programs with learning test cases. Second step is finding the correct program with the most similar structure to the incorrect program. Third step is localizing the fixed location by matching a correct and incorrect program. Last fourth step is repairing the fixed location by using the correct program to generate feedback. Existing AF techniques cannot generate feedback for complex programs. One of the complex programs is a multiple function program. As mentioned earlier, AFG must find the correct program with the similar structure to the incorrect program by program matching to generate feedback. However, in multiple function programs, the function count and names can be written differently for each student. Therefore, existing AFG techniques cannot match programs in multiple function programs and cannot generate feedback. There are 2 student programs for the same programming assignment. The left student program has 3 functions, but the right student program has only 2 functions, and the program has different function names. In the case of multiple functions, programs cannot be matched because the function count and names are different. Then how do multiple function programs match programs? For this answer, we have to transform the programs into a standardized format. Therefore, we transform the multiple function programs into single function programs. This is our motivating example. Feedback is generated through 2 processes. First process, standardization, is a method to transform a multiple function program into a single function program. And second process, repair, is a method of generating feedback by using the correct program to repair the incorrect program by replacing function and variable names. The figure shows the workflow of Munch that we propose. We take correct program, incorrect program, and test cases as input. Then through 5 steps, Munch generates feedback. Standardization process is divided into 2 steps, representation and inline functions. First, the source code of the program is represented as abstract syntax tree through the representation step, and the function invocation statement and the function code called by the function invocation statement are found through the function invocation node of the AST. And through the inline function step, function code is inlined into function invocation statement. However, if function code is inlined as it is, the output value may change or a compilation error may occur. Therefore, refactoring such as changing the variable name or changing the return statement is required. Therefore, we inline function code by refactoring the program with simple refactoring rules as shown in the following figure. The repair process is divided into 3 steps: function mapping, variable mapping, and replace. First, the function mapping step, the function names of the 2 programs are mapped by extracting the function call order in which the function code of each program was inlined. and the function mapping maps the reverse of the function call order. In the second variable mapping step, the variable names of the two programs are mapped using dynamic equivalence analysis. HDA infers the specification of the program by learning the program using test cases and extracting the change of variable values along the execution path. Variables with the same variable values according to the specification of the two programs deduced in this way are mapped. Finally, feedback is generated by replacing the function and variable names in the correct program and the incorrect program using the mapped information. To check the performance of MOOC, we collected programming assignment submission from real students in our Python course, and we collected 333 programs. Students can write programs with a variety of algorithms. Therefore, to generate feedback with the algorithms that are most similar to the student, we pair the programs with the most similar structure through the triad distance for the experiment. The table shows the result of our experiment, and as you can see, we generated feedback on 90% of the total of 202 incorrect programs. This is a discussion about our experiment result. MOOC appears by just replacing function and variable names. Therefore, it can generate a lot of feedback. And it might generate completely different feedback from the student algorithm, but our method generates feedback with the correct program that is most structurally similar to student program. Therefore, we expect it will be understandable to students. And MOOC cannot generate feedback in 10% of incorrect programs when mismapping the functions and variables. Mapping with dynamic equivalence analysis relies on program execution. Therefore, many high-quality test cases are required. However, there are not many test cases in the real world, and the experiment was also conducted with only 5 test cases. Our experiment result demonstrated MOOC is well at generating feedback for multiple function programs, and one of the more complex programs that traditional existing AFG techniques have not served. Thank you.